Welcome to the Nature Reviews Physics Machine Learning Research in Industry session. It is the last session of our series with Nature Reviews Physics and Turing. All the previous ones are recorded, as will this be, so this session is being recorded, and all sessions will be uploaded on the Alan Turing website in the next day or so. So you'll be able to see all the talks there. Okay. Afterwards, you'll get a free feedback form, and we very much welcome your feedback. But the idea is we have two 20-minute talks. First, Tien Liu and then Max Welling, both from Microsoft research area. And it's a new organization called AI for Science. And then we hope we will be joined by Anima Anandkumar from Caltech, but she's got some commitments which may delay her, but we hope she'll be joining us, and we'll have questions after all three talks. But if she doesn't join us, we'll have questions immediately after Max's talk. So I'm particularly interested in Microsoft's new organization and the fact that they now have AI for Science as an organization, and Tien Liu at Microsoft in Beijing has been working on machine learning and AI for many years, and has recently been moving towards AI for Science. And he and his team, for example, developed Graph-Hormer for material representations, which won the KDD Cup in 2021 on molecular property prediction, for example. But Tien has produced all sorts of interesting applications, from detecting particles in jets at the LHC in particle physics to looking at fluid dynamics and other areas. So we're very pleased to welcome Tien to this seminar, and what I'd like to do is ask Tien to present his talk now. Tien, welcome.
Yeah, sure. Thank you very much, Tony. Let me share my screen. So can you see it?
Yep, everything's fine.
Okay, great. Yeah, so thank you again, Tony, and hello, everyone. This is Tien Liu. I'm from Microsoft Research AI for Science. And for those who do not know me before, I prepared a one-page self-introduction. And you can see from the page, I have been working on the machine learning and AI area for almost 20 years, and started looking into computational biology and AI for Science 3 years ago. So it's really my great pleasure to be invited to this seminar and share my views on AI for Science, and also introduce some of our recent research along this very cool research direction. And as we all know, in the past decades, artificial intelligence has experienced a rapid development. So if you search AI plus human parity in a search engine, no matter which it is, you will see a lot of breaking news in the field of speech recognition, image understanding, machine translation, and many others. Actually, I'm quite proud that we, Microsoft Research, including my own team in Beijing, has contributed a lot to these amazing results. But furthermore, in recent years, with the emergence of big data, big model, and also big compute, foundation models like GPT-3 or DALL-E 2 have demonstrated their unbelievable capabilities in language and image generation. However, if we revisit all these successes, we will find that they are mostly mimicking humans' vision, speech, and language capabilities. But these capabilities are very basic in a stack of human intelligence. As human beings, we are unique, not because of these capabilities, but because our courage and ability to discover and change the world around us. So speaking of the world, we human beings are actually a very paltry existence in the world. So from the microscopic view, we are composed by trillions of cells, and each cell consists of trillions of items. The magic interaction between these particles define who we are and how we behave. And from the telescopic view, we are just one of the millions of species on the Earth, and our Earth is just one of the trillions of planets in the universe. So only focusing on ourselves is somehow too narrow. If we want AI to really possess human-level intelligence, it must be able to mimic or even exceed our capability in discovering and changing the world. So actually, discovering and changing the world have been the dream for numerous scientists in the long history of our human society. However, there are still many unknowns and probably more and more in the scientific domain waiting for us to further discover. So this page shows the 125 modern scientific questions posted by the Science magazine in the special issue to celebrate its 125th anniversary. The fonts may be too small, but basically these questions are related to the mystery of the universe, the code of life, and the sustainable growth of our human beings. So Jim Gray, a Turing Award winner and also a former Microsoft technical fellow, categorized the historical evolution of scientific discovery through 4 paradigms. First, with our origin dating back thousands of years, the first paradigm was purely empirical and based on direct observations of natural phenomena. And the second paradigm was characterized by theoretical models of nature, such as Newton's law of motion and Maxwell's equations of electrodynamics. Derived by introduction from empirical observations, such equations allow us to generalize to a much broader range of situations. But while these equations could be solved analytically for simple scenarios, it was not until the development of digital computers that they could be solved in a more general and scalable manner, leading to the third paradigm based on numerical computations. And by the dawn of 21st century, computations was again transforming science. This time, through the ability to collect, store, and process large volumes of data using machine learning, leading to the fourth paradigm of data-intensive scientific discovery. So all these 4 paradigms are complementary to each other and coexist. And today, we are going to talk about a newly emerged paradigm for scientific discovery, which we call AI for science. It is an organic combination of the previous 4 paradigms and powered by the recent breakthroughs in the field of AI. So with AI for science, we have the opportunity to make scientific discoveries more automated and more scalable than ever. Next, I will introduce my own understanding on what AI for science really means and discuss its relationship with the previous 4 paradigms. So in my opinion, AI for science really represents a holistic view of scientific discovery, which can be represented by this very simple formula. Here, I use capital X to represent the physical world around us. And based on existing scientific laws, we can use some governing equations to explain X, and can use AI methods to solve these equations and deduce what will happen in the future. Here I use X theta to represent this process, which can be regarded as an AI-enhanced version of the second and third paradigms of scientific discovery. I call this part the first component of AI for science. And on the other hand, we also have to acknowledge that our scientific knowledge, our scientific knowledge is limited, and there must be a residual epsilon between X and X theta. And this residue can be captured by experimental data and can also be analyzed by AI algorithms. This corresponds to the fourth paradigm, refined by the recent breakthroughs in the field of AI, like deep learning, reinforcement learning, and large-scale foundation models. I call this the second component of AI for science. And furthermore, if our goal is not to simply mine the experimental data for its own sake, but to discover unknown science, like new equations, we will have the opportunity to enrich our known science by AI and form a closed loop of scientific discovery. This could be considered as an AI-enhanced version of the first and second paradigm, which I call the third component of AI for science. So because AI for science really goes beyond the 4 paradigms and can enable new capabilities, we believe it is well-deserved to be called the fifth paradigm. Next, I will elaborate more on the three components of AI for science and introduce our corresponding research works. So, okay, now let's first have a deep dive into the first paradigm of AI for science, which is learning from equations. So actually, scientific equations play a very important role in AI for science. However, the way that we deal with these equations is very different from the second and third paradigms. Instead of using numerical solvers to obtain the solutions of these equations, we have brand new ways of leveraging them. So first, we can define a loss function or a regularization atom for the AI model training by examining whether the equations hold for the current solution given by the AI model. This is very powerful, since examining whether an equation holds or not is exponentially simpler than solving that equation. And second, and the most straightforward approach is to use the solution of the equation given by the numerical solver as a training data or ground truth for the AI model. In this way, numerical solvers are the simulator of the world, and the AI tries to learn an emulator as its efficient surrogate. Please note that the data generated by the numerical solver is perfectly labeled, and its quantity is limited only by the computational budgets. Once the AI emulator is trained, it can be used to solve further equations in a much faster manner, probably by several orders of magnitude. So here I will introduce two pieces of our research works to demonstrate how we could learn from equations. First, our team proposed a novel AI model called Graphomer last year. It was designed to predict the properties like total energy given a molecular graph. Previously, people usually use graph neural networks for this purpose. However, we know that the expressiveness of graph neural networks is somehow limited, and one will usually suffer from the oversmoothing problem when the network becomes deep. In contrast, in our work, we adopted the transformer architecture, which has a significantly better expressiveness, and then we capture the topological and the relational information between items in the molecular graph using the positional encoding trick. We use massive molecular data whose total energy was computed by the density functional theory to pre-train this Graphomer model. With such a pre-trained Graphomer model, we achieved the best performance on many downstream tasks, like the KDD Cup 2021 or molecular property prediction and the Open Catalyst Challenge 2021. And based on Graphomer and several other innovations, we have built a highly scalable and accurate biomolecular dynamic simulation system. With such a system, we simulated the dynamics of the spike protein of SARS-CoV-2 and gained some novel insights into this virus. For example, we found the NTD part of the spike protein of SARS-CoV-2 has a wedge effect, and its wedge in and wedge out will affect the up and down position of the RBD part, and thus the open and closed conformation of the overall spike protein. Such a conformation change of the spike protein will affect the infectivity of the virus and may serve as a potential target for COVID drug discovery. So this result was published as a cover page article in Advanced Theory and Simulation and got quite a lot of attention from the research community. And the other work I want to introduce was related to fluid dynamic simulation. In this field, there is a very famous partial differential equation called the Navier-Stokes equation, or NSE. This equation is famous because its mathematical properties is still a mystery to scientists. More specifically, the existence and smoothness of its solution is unknown, which is one of the Millennium Prize problems. So as a consequence, NSE is very hard to solve in practice, even if people have developed many numerical solvers for that. And in recent years, there is a new line of research called physics-informed neural network, or PIN, which can be used to solve PDEs in a much more efficient manner. The idea is to define the loss function of the neural network as whether the current solution satisfies the target PDE. However, when we use this framework, this PIN framework, to solve NSE, we will encounter some major challenges. Somehow, when we use the differential form of the NSE to define the loss function, we have already assumed its solution to be differentiable and even smooth. Otherwise, the derivative calculation process during the learning procedure will be very unstable, and the learning process might eventually diverge. However, as we mentioned earlier, there is no guarantee on a smooth solution for the NIC. So as a result, PIN performs badly on some singular NICs, like the Lamb-Olszyn vortex. To tackle this challenge, we proposed a novel framework in which, instead of using the differential form of the NIC as a loss function, we use an integral form based on an equivalent stochastic version of the NIC. In mathematical words, we are now changing from seeking the strong solution of the NIC to finding its weak solutions. With this change, we can achieve some very stable training process and much better accuracy than PIN for those hard NIC configurations with singular initial boundary conditions and other tough situations. At the same time, similar to PIN, our method is much more efficient than traditional numerical solver. Okay, next I will talk about the second component of AI for science, which is learning from experimental data or experimental observations. Basically, I think there are many kinds of observations that we can leverage. For example, there are massive experimental data being constantly generated, like the 15 petabyte JET data generated by LHC per year, and the over 40 exabytes omic data to be generated by 2025. On the other hand, there are over 50 million peer-reviewed scientific articles published in the literature. So no single scientist has the capacity and the time to analyze all these massive data, read all those papers to gain the necessary insights. And the traditional machine learning methods developed for the fourth paradigm also have their limitations in dealing with such massive data. First, many such machine learning methods are designed in a task-specific manner and cannot benefit from the scale effect. And second, many such machine learning methods are purely data-driven, and what they learn might be non-physical at all. Considering these limitations, we see a disruptive opportunity by using the foundation model or other advanced AI technologies developed in recent years. So let me give you some example how we really handle these challenges. So first, to handle the first limitation, which is the scaling effect of the machine learning model, we can leverage large-scale language models like GPT-3 to summarize and understand scientific papers, which can lay down a foundation for many different downstream tasks. Actually, we have a trial in which we pre-trained a language model from the biology papers on PubMed. And then in order to convert the information contained in these papers and also in this pre-trained language model to structured knowledge, we developed a double prompt mechanism. I will not really talk about too many details here, but basically by using this pre-trained scientific language model and the double prompt mechanism, we can extract knowledge from the published peer-reviewed papers very effectively. For example, given this paragraph, as shown on the left of the slide, our model can help extract some really meaningful knowledge. For example, based on this paragraph, our model can tell us that the interaction between the NTE1 and the insulin degrading enzyme is inhibition. So this is kind of a relational information extraction in a very effective manner. One appealing point of such a scientific language model is that it is automated and it can be easily scaled up. So it will be able to provide a strong information source for people to do new research. With this kind of scientific language model or foundation model, we are not just standing on the shoulders of some giant, but on the shoulders of almost every scientist in the literature. And to address the second limitation, when learning from data, we need to be aware of the governing equations behind the data and make a specific design in the AI model, such as imposing the equivariance requirement. to ensure that what we learn are really physical. I will give an example here, and I think Max will show even more examples in his talk. My example is about the analysis of jet data generated by LHC for new particle detection. However, this task is non-trivial because the properties of the particles, such as the mass and the helicity, are all need to be Lorentz group equivariance according to the governing equation. If we simply apply an existing AI model like a graph neural network developed for other applications, it is almost impossible to have this equivariance guarantee. To tackle this challenge, we propose a new AI model called LorentzNet. With carefully designed architecture, we can prove that LorentzNet is always Lorentz group equivariant. We tested this new model on the task of top quark tagging, and the experimental results show that it can significantly outperform other AI models without Lorentz equivariance guarantee, and is several orders of magnitude faster than traditional numerical solver. This work was published in the Journal of High Energy Physics and was regarded as the state-of-the-art of equivariant learning for particle physics by a famous white paper named The Future of Particle Physics. Okay, last but not least, let's move on to the third component of AI for science and see how AI could help close the loop of scientific discovery. Actually, this is kind of AI automation of the process that physicists discover new laws from experimental observations. A common approach is to consider whether the existing laws can perfectly explain the new observations. If not, either there are problems or noises in the data, or there is the opportunity to discover new laws. For example, as we all know, conversation loss is quite common. However, if the data contains some components which is non-conservative, then there may be a good chance for new science discovery. With this in mind, we designed a two-branch AI model with a conservative branch and a non-conservative branch. We then use this model to fit the experimental data. After that, we use a symbolic regression to explain the signals captured by the non-conservative branch. We use this model to learn from some publicly available experimental data for double pendulum and Neptune and gravitational radiation. And the symbolic regression expressions discovered by our model, as you can see from the table, are very close to those well-known physical laws. This is kind of a verification of the effectiveness of this methodology. And we really hope in this future, this AI method can be used to discover some new laws that we have never seen from the future experimental data and help enrich our scientific knowledge. Okay, so up to now, I have briefly introduced the concept of AI for science and the three components of it. We believe AI for science is going to make a huge impact on the natural science community, especially in explaining the secret of life and to ensure the environmental sustainability. Along these two directions, we are looking at several key applications as shown in these slides. And also we have been doing some quite interesting research as shown on the slides too. So if you have interest, please feel free to read these papers and contact us, and we look forward to collaborating with all of you. And considering that the AI for science is such an important new research paradigm, we at Microsoft believe that it deserves a dedicated organization to focus on it. So in July this year, we announced the establishment of a new lab in Microsoft Research, which we call Microsoft Research AI for Science, led by Chris Bishop. Both Max and I, we are founding members of this lab. If you share the same dream with us, you are highly encouraged to join forces with us. So let's build a better world together through AI for Science research. Thank you. That's all for my sharing. And really, thank you very much for your attention. Thanks.
Thank you very much, Tien. A very exciting and entertaining talk. I think there's a lot to think about. So I should just like to remind people that please ask your questions, and in the chat at the beginning, you'll see that Zainab has put up the Slido link that you can ask questions, and she'll make sure you got that. So questions on Slido. So thank you very much indeed, Tien. The interesting thing was I worked with Jim Gray when I was at Microsoft Research, and we wrote the Fourth Paradigm book, and I had difficulty. Jim was the only multidisciplinary group in Microsoft Research. And in order, when Jim died, it was very difficult to find someone to take over. And the person who I persuaded was David Heckerman, who used to lead the machine learning group. So we looked at a very small piece of your broad agenda, and it's really a much more broad and exciting agenda. And I personally am very pleased to see that. So we look forward to your questions in a moment. So what I'd like to do now is go straight to Max Welling, who has done many things. He did a PhD under Nobel Prize winner Gerard 't Hooft on gauge theories and solving the questions of the universe. And he's now gone and done many things. He's worked with Geoffrey Hinton, who was one of the pioneers of deep learning, as most of you know, and he has been at the University of Amsterdam with his group on AI and working with industry, and now he's actually moved into Microsoft, as you can see, but he's been doing extremely exciting stuff in the general area of surrogates, I would say, at the moment. So we're looking forward to hearing about that. And his title is Boosting Scientific Discovery Using Machine Learning. So Max, we look forward to hearing from you. Thanks.
Thank you very much, Tony, for the kind introduction. I'll share my screen now. Let me know if that worked.
That works just fine. You could do the whole screen, yes. That's it.
Yep, there we go.
Okay. Thank you.
Yeah, so I'm very excited to be here and follow Tien. I'm also from Microsoft Research AI for Science. There's a new lab in Amsterdam that we just started. And I also still have 1 day a week at the University of Amsterdam. So I'll be talking today about, first I'll talk about a brief introduction in deep learning. Then I'll talk about AI for science and deep learning for molecules a bit more. And I'll highlight some of the recent projects that we did. And then I'll have some concluding remarks. And by the way, this beautiful picture, which illustrates basically doing deep learning on a manifold, a sphere in this case. It was created by Maurice Weiler, one of my students, and it involves gauge theories, actually. So part one, it will not have escaped you that deep learning is having a huge impact in society and in science and in engineering. It started around 2010 when speech recognition was sort of stalling, and with the introduction of deep architectures, the error rate started dropping fast again, to the point that your phone now actually understands you when you talk to it. In 2012, something similar happened by the same group, Geoff Hinton's group, where they participated in a challenge, in an image recognition challenge, ImageNet, and they, by introducing deep learning, halved the error rate on that competition. And these days, you can have deep learning explain a joke to you, which is in itself a joke, I think, but very interesting. It is doing a very good job. And it can also transform basically a prompt, a piece of text, into an interesting and rather creative image, actually, or these days, actually even a video. Now, these technologies have now also extended themselves to science. And this is where I think things get very exciting, because the applications there are incredibly disruptive and exciting. We all know the great work by DeepMind, called AlphaFold, where basically an amino acid sequence at the input of a neural network is transformed into three-dimensional structure of a protein, very important for biology. Also, work by EPFL with DeepMind, a sort of nuclear fusion reactor with a plasma in it, and reinforcement learning was used to control the plasma and keep it stable. And these days, and I'll talk more about that in the rest of my talk, there's also now new technologies to create stable, real molecules out of thin air that might, for instance, target diseases. So a little bit about what is deep learning. I'm not going to say anything deep about it, but there's the architecture. It's called a CNN, a convolutional neural network, first introduced by Jan LeCun. And I would say that one of the structures that is most interesting for molecular science is actually a graph neural network, like Graph-Former that Tien was talking about, where nodes, which you can think of as atoms, are exchanging messages with each other to sort of compute some properties about the molecule. And one major important inductive bias is basically the idea that the world is invariant under rotations and translations and sometimes also some other symmetries, and building these symmetries into these neural networks has been a topic of the group in Amsterdam. So if you like equations, I offer here an equation on the left. This is basically the equations for a graph neural network where we have some internal representations, h, some distance, these are all invariants under rotations. And so messages are being exchanged between these sort of scalar quantities and these vector quantities. This could be the position of the velocity. And the whole thing needs to be equivariant under rotations, which is sort of illustrated here, which basically means if I first process the information on the graph and then rotate it, it should be the same as first rotating and then processing the information on the graph. And this is quite similar to what Tien showed as well with his, there's a Lord net and there is the net for the Lorentz transformations, which are sort of also similarly equivariant. Okay, let me now talk about sort of AI for science. So of course, science span an enormous spatial temporal scale from particle physics at the picometer and femtosecond scale all the way up to light years and giga years for astrophysics. And in the middle, at the scale where we live, or below, slightly below the scale where we live, we have molecules, and at the scale where we live, we have plasmas and fluids that are also of core interest to the AI for Science team, as I will talk about more. And I'm in particular interested in some of these topics. Like here's, for instance, partial differential equations. What I find fascinating is that basically all of the natural sciences use partial differential equations to explain the world, where machine learners never made much use of them. And what we're now seeing is that not only are we using machine learning to accelerate the numerical solving or the solution, finding the solution of these partial differential equations, we're also finding that partial differential equations are embedded into neural networks as inductive biases to build better neural networks about the world. And in particular, I like to highlight this work. This is by Anima Anandkumar, who will hopefully also join us. Beautiful work about modeling sort of the weather patterns on the Earth using deep learning technology. In their case, it's a FNO framework where they forecast basically the storms as they're happening. We've ourselves also contributed with this group of people a model which is called Clifford neural networks for PDE modeling, where we use certain mathematical structures to also try to accelerate the solution of a PDE. But molecules are of their own sort of interest. It's kind of fascinating that everything around us that you can touch, basically, or even the gases and the liquids and the solids, they're all made of molecules. Now, there's of course exceptions. There's 4 fundamental forces like gravity that is not made of molecules. Of course, if you put enough energy in them in an accelerator or something, then of course you create plasmas or quarks or leptons or stuff like that. But mostly everything we see in normal day life is made of molecules. And if we can understand molecules and simulate them better, we could be at the root of solving many challenges that we face today, for instance, in health and in climate. So here's a few examples that I want to highlight. There's drug discovery, where we try to sort of use a small molecule like a ligand to fit it in some pocket of a protein that is important for a disease to work. And so that way we want to neutralize the disease. Photovoltaics, where we try to turn light into energy using photocells. Also molecules play a very important role in these materials. Better lubricants to reduce friction, and 20% of all the energy is lost due to friction. Building and designing new catalysts, for instance, to split water into hydrogen and oxygen. But there's many more reactions that we like to improve the rates for instance, nitrogen fixation, which is also very important for fertilizer, but also for storing energy and hydrogen. And of course, there's also whole cell modeling. Okay, so molecules basically represent a huge opportunity. And I want to just mention that, in human development, we have named our ages in which we lived basically after the molecules that we use, right? We lived in a Stone Age, in a Bronze Age, in an Iron Age, and these days you could argue we live in a Plastic Age. And so what would happen if we could make materials basically on demand? So you tell me precisely the properties that you want your material to have. For instance, it should kill this particular disease, or it should capture carbon out of the air, or it should be like plastic, but it should immediately sort of break down when you throw it into your garden. There's many of these properties that you might like. And what if we could just create them on demand? The world would really dramatically change. And I think we are slowly starting to move into an era where this is going to be possible. There's the natural sciences, which have evolved to be spectacularly mature, like in condensed matter physics and computational chemistry and molecular biology. At the same time, the modeling technologies like computational science, machine learning, and hopefully in the future quantum computing are going to contribute to that process. And then there's the applications like health, the energy transition, and sustainability, which are pooling on these technologies to feed them with funding and inspiration in some sense. So I think we might see that we're at the beginning of what could be called a golden age of designing new materials, chemicals, catalysts, and drugs. Now, Tien already talked about the fifth paradigm of scientific discovery, and I'm going to repeat myself a little bit here. So if you think about it this way, so the first paradigm, if you wish, was trial and error, experimentation. You build an airplane and you see if it flies. Around, the fourth paradigm is, well, you actually build a model and you put it in a wind tunnel and you collect lots and lots of data, and then build better models around that. So the fifth paradigm is really you design the entire plane in a computer in silico. So basically you model the flow of air over the wings using the Navier-Stokes equations, the stresses on the body and the wings of the plane completely in your computer. You design your plane and then you just build it and fly it. So that's also the dream for molecular science. So first we had trial and error, then we built lots of data, lots of models around data. But in this sort of last new paradigm, we're going to actually simulate in our computer the molecules themselves from the laws of physics, which in turn create data, which will feed back into machine learning models, which can then accelerate that. So simulating molecules is actually, it doesn't look difficult if you look at it from this picture. There's like a bunch of classical beads on a graph structure that are interacting with each other. And you just need 17th century sort of physics and Newtonian dynamics to move this stuff forward in time. But there's many challenges, and the two biggest ones are, this is a chaotic system, a nonlinear dynamical system. So it's you have sensitivity to small changes in the initial conditions. but also, even to compute one step forward, you need to compute the forces on each one of these atoms. And there is this electron cloud, which is around the molecule, which really can only be described by quantum mechanics. But unfortunately, quantum mechanics is exponentially complex in the number of electrons. And so you very quickly hit a computational wall. Now, the way that the fifth paradigm tries to circumvent that is to by basically recycling the data so that we create through these simulations. So let's say we do an expensive step in the simulation using quantum mechanics and all this and other things. That data is now not thrown away. It's stored in a database. And then models, which are called force field models, are being trained to then accelerate the movement of these molecules next time when we get to similar situations, right? So we have neural networks which now circumvent or shortcut the quantum mechanical calculation. And basically the grand vision is some kind of search engine for molecules. It's not really a good term because it's not searching for existing molecules, but it could also be searching through molecules which have never ever been considered or created. And so we have two forward processes. We can simulate either with the laws of physics, which is slow but accurate. We can use our sort of surrogate models, neural networks, which are fast, but perhaps not everywhere as accurate. But I would argue that the sort of the big challenge and the sort of the great prize is to go in the reverse direction, which basically means that you give me the properties that you desire, right? And then the neural network will generate, using a generative model, will generate the molecules which have those particular properties. So let's dig into that particular idea a little bit more, this inverse design. And so here's a first model that was developed by these very smart students here, Emile, Victor, and Clément. And that's based on some of these really strong models that are being used for language and image generation. It's called a diffusion model. We of course made it equivariant to make sure that it respects all the obvious sort of symmetries of nature, which is rotation and translation invariance. And these models sort of at a high level work as follows. You start with a blob, with a noisy blob of random number and random types of atoms. And then through a sort of a denoising process, you then create out of thin air molecules which are stable and realistic, right? And then there's the inverse process, which is the noisy process, which is basically adding noise until you get to this blob, and you learn to denoise that into realistic molecules. And that's not just good for generating images and videos on text prompts, but it's actually also good for generating molecules. And here you see a few examples of reasonably large molecules that were being generated by this system, and they were also being tested for actually being realistic. And here's a little bit of a sort of an animation of how that process works, right? So here is the blob, and the blob denoises itself into a stable molecule. Fun to watch. Okay, so a second model that we looked at was basically this diffusion model for linker prediction. So I will be talking about this molecular linker design. Here, sort of the holy grail of generative models is to do conditional generation, where I just give you a bunch of properties, and then from those properties, you generate the molecule with those properties. That's actually very hard. But what we're going to do here is to say, let's fixate a context, a pocket, let's say, of a protein, and then have a diffusion model generate a ligand which fits nicely into this pocket and could neutralize it, let's say, if it were a disease. And in particular, we looked at sort of a slightly more general problem where you give me a bunch of fragments, an arbitrary bunch of fragments, which will actually fit in particular parts of the pocket. And then basically you generate, using your diffusion model, the pieces which connect these fragments into a realistic molecule. And so here you see a few examples of how that particular process works. Okay, so and then the last example that I wanted to quickly talk about is stochastic optimal control for sampling transition paths. This is with these very smart people here. And the idea here is, I like to call this Project Sisyphus. So Sisyphus was this guy who needed to, push this rock up a hill, and by the time he was up there, it came rolling down again. He had to start again. It's a little bit. That's a little bit like waiting for a reaction to happen in your computer, right? Because you want something to happen, a confirmation change or a actual, an actual chemical reaction, but it takes a very, very, very long time if you just simulate. So what you really need to do is to use to add forces to push the ball or the rock or the molecule over the hill, over the energy hill. And so here you see an example of where we sort of used reinforcement learning to force the molecule to get from one conformer to another conformer. And here's two more examples that I wanted to show. Oh. Yeah, this one should also start, but it doesn't. But anyway, so there's these molecules which are, gently pushed to go from one conformer state to another conformation state, and then we can track the energy. Not sure why this thing is not really running, but that's it. Okay, so then I'll conclude. So we are clearly seeing that deep learning is having a huge impact in language and image and video analysis. We can now generate images from free text and even videos from free text. What we're now seeing is that same set of technologies can be transferred to the natural sciences, and in particular molecular sciences. And I believe, at AI for Science at Microsoft Research, we believe, or we bet even on, that that's going to be the next field to be disrupted by deep learning. There's huge opportunities in terms of societal goals. Now, I'm personally quite worried that we are driving towards the edge of a cliff without braking very hard. I think besides many other things, these technologies could help, for instance, to pull carbon out of the air. So there's lots of sustainability targets like carbon capture, battery materials, hydrogen production, synthetic fuels, nitrogen fixation, and many more. But also in health, in terms of drug discovery or new vaccines or antibiotics that work against resistant bacteria, etc. Okay, I need to push my alarm off. Right. But besides sort of very interesting societal goals, there's also huge economic opportunities. I believe that there's going to develop a huge economy around carbon capture, new materials, catalysis, and in pharma, just because these things are going to become possible, and it's hard to even imagine the things that can happen once we can design materials on demand. And I'll stop there, and thank you very much.
Thank you very much, Max. That was a fascinating overview of the challenges that you've been attacking, and it's really exciting. I have to admit, it looks really good. So we'll have questions, so don't forget to put your questions in Slido, and we'll take them at the end. But I'm very pleased to hear that Anima is here all the way from Caltech, and she has arrived in time to give her talk, which is really good. So Anima is the Bren Professor in the Computational Mathematical Sciences Department at Caltech, and she's also a Director of Machine Learning at NVIDIA. So she has both the academic and the commercial aspects, and she co-leads at Caltech the AI for Science Center. So in particular, she's been doing some very exciting work on tensor representations and tensor architectures. So Anima, I'm very pleased that you could make it, and can I ask you to give your presentation? Thank you.
Thank you, Tony, and it's a pleasure to be here. So you saw the previous speakers, I saw Max finishing his talk on molecular representations, tackling climate change. So those are very much at the heart of what I'll be saying as well. So I think you've already got a great foundation to begin with. Yeah, I mean, to me, it's very exciting as an AI researcher to incorporate AI into so many areas of sciences. So how can we herald new breakthroughs that wasn't possible before? So to me, I think one aspect that is so important to us today is being able to model climate of the future, right? So we know climate change is here, but we need to be able to precisely model the global climate decades from now in order to precisely be able to understand how, to what extent climate change is going to happen, especially in different regions, regions like Middle East, which may become uninhabitable. So these aspects are really important. And one aspect that is really stopping us today from doing that is the ability to capture these low-lying clouds called the stratocumulus clouds. So the ability to capture them is so essential. And why is this challenging? Because currently we are doing this by using partial differential equation solvers. And in order to capture these physical processes accurately from ground up through these numerical methods requires us to go to very fine grids. Both spatial and temporal grids need to be very fine because these are fine scale features we need to capture. And the hope is, with AI, can we overcome that? And this is not just a nice intellectual exercise, right? Right now, we are not able to do this because ultimately, if we need to capture these low-lying clouds effectively with numerical methods, we need to be able to go down to 1 meter resolution globally and simulate this at 1 second intervals. And this is just untenable with current computational, hardware. So it's predicted, I think, at Tapio Schneider, my colleague here at Caltech, who heads the Climate Project, estimates that you require about 100 billion times more computing than what we have today. So, so we're not able to do this today. We are only able to do coarser resolutions, and that brings with it uncertainties. And that is not only true in the climate realm, but also in other areas like molecular modeling. Max showed you some of the frameworks of how we could use generative models to generate molecules. But if we want to precisely predict all the properties of underlying molecules, right, it's not just the graph structure that matters. What matters are these interactions between the atoms, especially the electrons. You are getting quantum effects, so we need to look at wave functions. And if you try to do the Schrodinger's equations precisely, if you do it brute force, it's estimated that you would need to take longer than the age of the universe with current supercomputers, even for just computing it on 100 electrons. So again, another impossibly hard problem with what computational hardware we have today. And so that's the hope. Machine learning can really help us make a big jump from what is possible today. We are seeing speed ups of as much as 1 million times compared to numerical solvers. And that combines both, the aspects of accelerated computing. Many of the current solvers are on CPUs today, and it is quite an effort to get them to GPUs and other accelerated computing hardware. And we also need to, on top of it, design careful algorithms to scale up and out on supercomputers. And what we can do with machine learning is get the gains, all of this almost directly, because we have highly optimized frameworks to accelerate machine learning. And on top of it, we get further leap because we need we can get these feature transformations. So instead of trying to compute these cloud processes in the standard domain where you need a fine grid, the hope is by learning the appropriate feature transformations, we can do that much faster. So we are not limited by this fine grid. And that's the hope that machine learning can enable that. And we've developed AI frameworks that can do this very effectively. So let me get into that. So we call this method Fourier neural operator. So this is, in fact, a general framework that goes beyond neural networks. So how is a neural network defined, right? So you give an input in a certain domain and a certain size. So you'll give the input at a fixed resolution, and your test data will also be at the same resolution. So if you're doing an image-related task, let's say classification or segmentation, so you typically fix the resolution and give data only at that fixed resolution. So on the other hand, if you ask it to have an image at a different resolution, right, it's not a valid input for a standard neural network. And that's where the neural operator generalizes this notion of neural networks in finite dimensions to now infinite dimensions. So what we want is the ability for neural operator to be operating at any resolution at any grid. So once the neural operator is trained, it can work on any different discretization from the input data, from the training data. And with that, the ability to now seamlessly change grid points, right? Go to a different shape of grid, different resolution of grid, and without having to retrain. And that's because the way we capture this neural operator is to define it as learning a mapping between function spaces. So if you think of a partial differential equation, typically the input is a function, right? It's the initial boundary conditions, which are functions defined in the domain. So you can have that function be any point in the domain. And similarly, the output is the solution operator, right? So it's the solution function rather at any point in the domain. And this mapping is the solution operator. And so our goal is to learn that instead of just a fixed discretization or fixed resolution inputs and outputs like in a standard neural network. And the other aspect we really require our neural operators to be is discretization invariance. So if it's learning now an operator that is mapping between function spaces, we need to have the ability to query at any point in the domain, right? So once it's trained with given parameterization, we should not need to retrain just to query at any point in the domain. So the training data can have a very different discretization from test data. And at the same time, we need a sort of consistency, meaning if you keep refining your grid or mesh, in the limit, it should converge, right? So the idea is you can start, once you've trained the neural operator, you can operate it at any different kinds of grids here. And the output that the neural operator gives you should ultimately converge. And so that's a kind of consistency that we can ultimately hope to approximate the underlying operator in the limit. And so how do we arrive at this? So the way we went about building this is to use the same notions as in neural networks, but now instead of operating in fixed dimensions, we want this to be operators in function spaces. So we know standard neural networks, you can have a linear operation followed by nonlinearity. And one of the popular linear operations is convolution, right? So you design filters of fixed sizes in a convolutional neural network. But on the other hand, instead of these fixed size filters that are local in a neural network, we want a convolution operator or an integral operator. And so, which is still linear, but it's an operator. And once we combine this with nonlinearity, we have an expressive model that can capture general nonlinear continuous operators. And the idea now is, how do we design this convolutional operator effectively, right? So even if the input is just discretized data, can we have it learn a convolution operator instead of just convolution in fixed dimensions? And the way we go about doing this is to ensure that this convolution should be discretization invariant, meaning it doesn't just work on a fixed resolution, it can work at any resolution, and in the limit, it should converge to the continuous convolution on the domain. And so the Fourier operation is one effective way to do this. We also have other methods, but here I'll focus on the Fourier neural operator. And the way we think about doing this is, convolution in the standard domain becomes multiplication or element-wise multiplication in the Fourier domain. And so we can now transform convolution operation into one of learning weights in the frequency domain. And we can then go back to the standard domain and do nonlinear operations and continue this over several layers as needed. So the key is now, if you think about Fourier transform, you can in principle do Fourier transform on any domain, right? So it can be regular or irregular, it can be discrete or continuous. And so that's why if you now do Fourier transform at different resolutions, in the limit, it'll converge to the continuous Fourier transform. And that's how we can approximate the continuous convolution effectively. And so that's the underlying principle. It's very much taking from signal processing 101, that we can efficiently compute these convolution operations in the Fourier domain. And the reason that this also becomes very efficient is if we implement Fourier transform through fast Fourier transforms, we also have a very fast operation. And the other benefit of this is it's a global convolution, right? So unlike our standard convolutional neural networks, which design filters that are only local, this Fourier transform is global. And a lot of phenomena that we think about, whether it's climate modeling, whether it's material properties, require these global correlations, And so that's another aspect that these Fourier neural operators capture very well. And so you see that here in this example demonstrating the discretization invariance. So we trained it only on coarse resolution data. This was a 64 by 64 grid, I think, spatially. And we directly evaluated, once the model is trained, we asked it to predict the fluid flow on a much finer resolution, and it's still able to do that well. And so that's the idea, that this enables zero-shot super resolution seamlessly and is built on a principal theory that we can approximate the underlying operator and not just functions in fixed dimensional spaces. And so now I want to show you how these methods perform in a range of domains and applications. For instance, we've done this for weather forecasting, and we see it's about 45,000 times faster than current numerical weather models. So very fast, but as accurate as them for a week and even longer. We also see the same model being able to capture extreme weather events like hurricanes. And so here you see the contour plot of this for high-speed winds, and see that it can accurately capture the trajectory. And the other benefit of this fast method is we can do very large number of ensemble members. So we can get good uncertainty calibration by the ability to do so, whereas with standard numerical weather models, because they're so expensive, you cannot have many ensemble members. Excuse me, sorry, and something's on my throat. So what you see here is the reason why this model is able to do so well compared to standard numerical methods is that it's trained on a large data set. We have lots of historical weather data that is not exploited by current numerical methods effectively. And at the same time, the Fourier neural operator enables us to capture much higher resolution than other standard AI models. People have done graph neural networks, UNets, and so on, but they fail at capturing the fine resolution. And that is so important to do longer term weather forecasting than what the previous methods were able to do. So this is also really crucial for handling climate change and asking how we can mitigate it. Carbon dioxide sequestration is going to be a big part of it. If we can capture carbon dioxide as it is being produced in various processes, or even ultimately one day directly from air, whichever the procedure is, ultimately we need to store it deep underground. And when we are doing that, we need to be able to understand how the water and carbon dioxide interact, and what is the gas saturation and how that evolves. And our method is able to do this in a 4-dimensional setting with multiple wells. So if you give us the permeability map, right, what is the rock structure, how permeable it is, and the configuration of the wells, we can do a nested Fourier neural operator. So essentially a local grid refining method with Fourier neural operator. And this is able to do this kind of simulations very fast. So here you can see the gas saturation evolving for over 30 years, and it's 100,000 times faster than the current numerical method. So this will allow us to do large-scale exploration of sites that are suitable for carbon capture and storage, as well as do good uncertainty prediction or quantification. So I want to quickly show you some of also the impact on molecules and chemistry. These are very much you'll see align with what Max has also shown before. So this was a large-scale effort that we did, an unprecedented billion-atom simulation. And here, what we wanted to study is how the coronavirus interacts with the respiratory aerosol. So we closely studied the spike protein structure and asked, how does it bind with the calcium ions from the respiratory aerosols? So what you see in yellow are the calcium ions from the respiratory aerosol, and we want to calculate its binding energy with the spike protein. And so this is where we used AI-based framework called OrbNet that can accurately do quantum level calculations and predict these binding energies much more accurately than the standard force field methods. And this is not possible with standard approaches like DFT, which is very expensive. So it's an unprecedented more than 1,000 atom calculation of quantum chemistry that wasn't possible before without the use of AI. So another aspect is also to be able to generate new molecules given certain constraints of what the properties should be. Max showed you great visualizations from the diffusion model. So a new aspect that we brought in here is also to be able to have retrievals, right? So you don't just have the model memorize to generate different molecules, but we also can give a database of molecules with different properties. So we can change the tasks. So, we can change from one disease to another, one kind of properties to another. And so we can give a database of current molecules, and they may only partially satisfy the properties required, but we can fuse that information with pre-trained molecular generation models, and those can be the diffusion models or any other models that are available. And so the idea of fusing data information from a database of existing molecules and their properties with pre-trained generative models, I think will be very powerful. And we've seen that in terms of the ability to even improve existing coronavirus drugs. For instance, here, this was the original coronavirus drug, and I've heard these polar contacts are really important for its effectiveness. And here we have our method improving these polar contacts compared to the original molecule. So this way we can improve upon existing drugs very effectively. Another aspect is also multimodal foundation models for science. And one aspect is to be able to seamlessly interact with natural language, right? This way we can ingest all the scientific articles that are published about molecules. And at the same time, we can relate it to the structure of the molecules. So we have now a model that knows both about the structure of molecules, as well as you can give it natural language instructions. So give me a molecule with more hydrogen bond acceptors compared to the input, and it will, improve upon the existing molecule. So you can seamlessly interact with this model in natural language and ingest as well all the knowledge that's present in scientific text. And here you can see that as well. You can give different kind of text prompts of what you want the molecule to look like, and it will edit the input molecule to look more like the molecule you want. And so for a lot of editing, molecular editing for different drug properties, structure-aware bioactivities, we can use this framework. So yeah, thank you. It's a pleasure to be here. I truly believe that the integration of AI and science is the future of science. We are in exciting times, and operator learning, I think, will play a big role to capture processes that are multi-scale. The fine-scale processes cannot be ignored. And so you cannot automatically coarsen the resolution in numerical methods. But that's where our frameworks that can learn features, but at the same time, do that in a discretization invariant manner that can go from just limiting to a fixed grid to being able to query at any point and have this discretization invariant property, I think is very crucial. Thank you.
Thank you very much, Anima. That was very exciting. And I think in the 3 talks we've heard, it's really been a dramatic view of AI for science. And it looks in a very exciting new generation. We now have questions, and please, questions on Anima's talk, could you put in Slido? And Zainab, can you summarize the questions, or shall I go to Slido and look at them? Maybe I'll go to Slido and look at them, right? Right. Okay, so there's a couple of questions which I'll come to in a moment. But first of all, I have a slightly more broad question. One of the things that I'm encouraged to see is that you all have big visions for molecular modeling and so on. It's unfortunate we can't get Pushmeet Kohli, an ex-colleague of mine at Microsoft a long time ago, who couldn't come to talk about DeepMind's contributions. But my concern as an academic is whether we can actually compete with a company doing research like NVIDIA, like Google, like Microsoft, if you're in academia, can you put together sort of multidisciplinary teams and the computing resources to be able to actually address these sort of problems? So I'd be interested just to start off by hearing your views on that particular question, and then I'll go back to the questions online. Okay?
I mean, in my view, it's, we shouldn't frame it as competition, right? But a great opportunity for collaboration. I know I see the opportunities for collaboration as unprecedented because industry is now looking into domains that previously weren't considered as profitable or something that, right, they could make an impact. And now it's all within reach. I think, the power of computation is immense, and in industry we have a lot more resources, but also the engineering prowess, right, to scale up these models. And at NVIDIA, our philosophy is to enable this ecosystem, and we have a history of working closely with universities, national labs, the large scale coronavirus modeling that I showed you was done in a highly interdisciplinary team, a lot of people from university, from the national lab and NVIDIA to help scale up. So I think these kind of interdisciplinary and interinstitutional collaborations are now much more possible. And companies, especially I can talk about NVIDIA as being very open in that. So everything we are doing, we are open sourcing. We are enabling the community. Our weather model is available. Even the trained model is available for people to build upon it. And so, yeah, I see that as a golden age for AI for science.
Very good. Anything for Max, Tien? You want to say a couple of words?
Yeah, I can say something. So I fully agree with what Anima is saying. Yet I've also heard people in academia express this worry to me. So of course, there's always, you can always do a lot of exploratory, more theoretical work to distinguish yourself. But I think some of the worries are that papers who don't have the bold numbers don't get published. And there's only one way to get the bold numbers in some domains, which is to actually have very large compute. And so I think we should maybe try to make that more fair in a way, maybe to start reporting the amount of compute power that you had available to reach these results, or maybe even showing a scaling curve where, with the number of compute hours you're putting in, how much did the results improve? And then, in order to compare that with a sort of a small lab with a few GPUs, you just sort of look at this curve where you are. And in that sense, it might become more fair. And at least it becomes maybe people become more conscious of the fact that, in some sense, you should certainly not just reject papers because they don't have the bold numbers.
Okay, yes, no, I see that. But you do, I think, need to get a breakthrough, to get a publication in Science or Nature. You need to have the results, and just scaling up virtually is not, I think, sufficient.
Yeah, I also want to add something. Yeah. So I think that's a very interesting discussion. Although I haven't been in the academia,
no, indeed.
After I got a PhD, I joined Microsoft. But I really can see some interesting trends. So I think natural science is a very different discipline that has been there for hundreds of years. A lot of very deep theory and science. So I think for AI for science, it must be kind of a collaboration between industry and academia. I cannot imagine that we can hire all those top natural scientists into companies. There must be a kind of collaboration. The industries have our advantages, like the computational resources and engineers, but the universities, national lab, they also have their very clear strengths. So that is a kind of a win-win situation. And second of all, I think in today's talks, I think both Max and Anima, they talked about a lot of sustainability, the green energy, and also the climate change. I think this sustainability or green research, it should also be something we consider seriously. So we should not really only fight for a good number using a lot of machines. We should think about how our research can be sustainable. How can we use the minimum energy to generate impact and meaningful progress? So this is not just a kind of a publication criterion, but every researchers, we need to really keep that in mind when we do research. This is my advice.
Okay, thank you very much. I have a question for you, Tien. What's your opinion on the topic of reduced order modeling?
Yeah, reduced order modeling. First of all, I'm not an expert on that, I have to say. But according to my very limited knowledge on that, if I'm wrong, please correct me. But I think the reduced order modeling is also kind of a efficient surrogate of the original problem. By lowering down the dimension, one can achieve a faster solver, but with the sacrifice of the accuracy, so something like that. And AI for science is, I think, share a very similar spirit in certain sense that we want to build a AI-based surrogate of the original problem, but we do not really design that in a heuristic way, so that there must be a trade-off between accuracy and the efficiency. Instead, AI for science trying to find that surrogate using optimization-based methods. So basically, we want to achieve an optimal surrogate, which hopefully will achieve a good balance between accuracy and efficiency, with several orders of magnitude faster. Yet, on the other hand, we do not really lose too much accuracy or even no accuracy loss. Yeah, that's the goal of AI for science. So that's is my shallow understanding of this question.
Better than mine. Anyway, that's good. I have a question for Anima. How useful is it to capture fine details such as stratocumulus for climate prediction? Is it really necessary, and why?
Yeah, I mean, cloud cover is so important to understand the process of climate and how that is going to change, because ultimately, everything from precipitation to how much the impact of carbon dioxide is determined by those low-lying clouds. So this is what scientists have determined, but the difficulty is, as I said, these are highly turbulent processes, and if you do not go up to the fine scale, you don't capture the dynamics of it. So you will be very off in terms of predicting its evolution if you don't go to fine scales with numerical methods.
Okay. And there is another question for all of you. What are the current limitations of the simulation of cell-level processes in biology? None of you talked very much about that, and I wondered if you had looked at things like that.
I mean, I would say lack of observational data and correlating that to scientific mechanisms, right? So, in some sense, the scientific mechanisms, from what I understand, are very simplistic and rudimentary because they mostly want to have biologists to get a sense of the mechanisms rather than accurately modeling them. And the other is the complexity of it, because where do you start? Do you start at the level of DNA? Do you start at the level of molecules? So if you try to piece all that together, it can get very complicated. And I think that's and the other is the context, right? I mean, you can't just take a cell in isolation and study it and expect it to have the same impact in vivo. So that's also the question of what kind of cell, where it will be placed, what properties do we want to study about the cell. So I was recently at the Human Immunome Summit, where the goal was precisely to overcome these barriers, because if we want to ultimately understand immune response and our immune system, is there a hope to build it from bottom up, or is there a way to directly just take the data in a more model-free manner, try to come up with predictions? And I think we should pursue both approaches.
One of the projects that I actually have been looking at with US Department of Energy, they have a collaboration with the National Cancer Institute, and they're looking at the RAF proteins, and they're doing a very detailed modeling. The difficulty is, of course, biology doesn't have the sort of PDEs and everything in detail that the other physical sciences have. But they have an interesting model, and since this particular chain is implicated in 30% of cancers, it's certainly an interesting area to do. And they have a multi-scale modeling, and they're using AI. I don't think they're using it in quite the way that you are, but it certainly might be worth you guys having a look at the Admiral project, and it's Lawrence Livermore Lab is the leader of that project. Anyway,
I'll take a look, certainly.
no, I think it might be worthwhile. I have a question for Max. What neural network captures of the quantum mechanical aspects in molecule searches? That's what the question is. So
I actually didn't get the question. So what quantum mechanical aspects?
Yes, it says, what does neural networks capture of the quantum mechanical aspects in molecular searches?
I'm not sure what a molecular search is, but maybe simulation.
No,
yeah, but I can say a few things. So so it depends a lot on the level of accuracy that you want, right? So there is, even within quantum, trying to simulate quantum mechanics, let's say for electronic structure, there is many levels of accuracy that you can try to achieve. There's a coupled cluster theory, which is typically thought of as a state of the art, and then there is DFT, which is cheaper. You can do it faster, but it's also less accurate. And then you can go all the way up to orbital free DFT, which is yet faster but less accurate. And then you can go to even try to capture force, the quantum mechanical effects in force fields. So at any time you would have to, if you want to train such a model, your challenge is that you will have to get your data from a more accurate model, right? So if you want to train a force field, you'll have to do a lot of DFT simulations in order to get the data for the force field. If you want to, so it's a similar thing happens in DFT. So if in DFT there's functionals that people really don't know what to write down there, physicists have written down many things that are reasonable. I think there's like thousands of functionals that people have written down. So one clear way to try is to learn these functionals from data, but for that you will have to get more accurate data from coupled cluster methods, which is super expensive to get. And so that's kind of the conundrum we are in, which is in one hand you want to put in inductive biases and sort of ideas about how quantum mechanics works, like limits and stuff like that, to reduce the amount of data and to learn these things. But at the same time, it's very expensive to learn these functionals or these forces. And then, of course, it's only valid for one particular set of molecules. And so if you want to then generalize away to another set of molecules, you have to, again, acquire new data. And it's like an ongoing process that's very expensive.
Thank you very much, Max. So one last question, and then I think we should wrap up. But the question is interesting. What could be the impact of quantum computing in AI for science? And I know that Microsoft and other companies like Google and so on have been investing in quantum computing, and I'd be interested to hear your thoughts. I have seen papers on quantum machine learning, for example.
Yeah, maybe I can say a quick thing and then let others say something. But so certainly we are building a quantum computer. And certainly we are thinking that quantum computers can have an impact on quantum chemistry. That's basically what Feynman already predicted, right? In some sense that, it is in some sense a controlled experiment that you're doing in a quantum computer, simulating quantum mechanics. And so it can sort of generate, very high accurate data and do highly accurate computations, basically, to compute, let's say, ground state energies of molecules. Now, it's not quite clear how useful it is and precisely what's the best way to use it to improve quantum sort of chemical calculations, but that's certainly what we predict and what many people with us predict, that that's going to be another revolution that might happen in I don't know, 10 to 20 year time frame or something like that.
Yeah.
Any other comments, Anima?
Yeah, at NVIDIA, we're focused on enabling large-scale simulation of this quantum computing, right, on classical computers, on GPUs. And at the same time, we're also doing research in terms of understanding what are avenues for quantum advantage. So where can we see an advantage in nearer term quantum computing compared to classical one? And this nearer term quantum computing will involve a mix of classical and quantum computing, so-called variational quantum algorithms, right? So how can we utilize the classical computing for optimizing quantum circuits, and then can they yield benefits? And so designing good algorithms for that, and then testing them at scale and simulating them on GPUs effectively. So we built CUDA framework for quantum called QQuantum, and that's being run in a lot of institutions at scale. So I think that's also important as we develop these quantum devices. How can we effectively simulate them? How can we develop better algorithms that do these hybrid computing effectively?
Tien,
anything to add, or are you happy?
Just to add a few things. So I agree with Max that if there is a usable quantum computer, of course we can do the quantum simulation in a much faster way, and we can just do those exact algorithm according to the first principle. But I think quantum computing and AI for science, they are not contradictory with each other. They are complementary with each other, actually. Even if we have a quantum computer, we can still use the concept of AI for science to derive a AI-based surrogate and develop that AI algorithm onto the quantum computer, which is, Tony, what you refer to quantum machine learning. So basically, they can all be the same loop and reinforce with each other. So that's the vision I can see.
Okay, yeah, well, I'm very interested to see what happens. We're just doing a new edition of the Feynman Lectures on Computation, which we included Feynman's original paper on quantum computers. But he also, one of the things I left out of the first edition was actually his interest in neural networks. So we put a little section about the discussions he had about neural networks, and you might find some of that interesting. Okay, I think we have to wrap up there, and I'm really grateful for all three of you putting in the time today, and I think it's been quite interesting, and I look forward to the follow-up, and whether or not you can attend those. I hope you can attend virtually or in person in the new year, but I recognize it must be difficult with your tough schedules. So thank you very much for joining us for the final talk in the Nature Reviews Physics series with Turing. And as I said, recordings of the previous sessions, including this one, will be available on the Alan Turing YouTube page very shortly. And we'd be very grateful if we'll send those attending, we'll send a short feedback survey, and we're very grateful to have comments or suggestions as to how we might organize the events in the new year when we wrap up and we produce a white paper on the discussions, which actually will include your wonderful, rather stimulating visions of the future. So thank you all. I'm very grateful for you coming, and well done. It was really a great session. Thank you very much.